All right, this is your example of what a self-paced lesson will be like. This is Mrs. Morel talking this time. Each time we do a video, it might be a different teacher talking, so we'll always introduce ourselves. So I'm Mrs. Morel. I teach in 720. Today our lesson is going to be number classification. Okay. Our objectives for today are going to be, our first thing we will be able to do is identify examples of each classification. All of our vocabulary words are the classifications that we're going to learn as we do our notes today. Our second objective will be to create examples showing our full extent of each classification. So some of these classifications have lots of parts to them, and we want to show each of those parts. Then we're going to classify numbers using more than one classification when needed. And that will be a lot when we do that in your practice work. Okay, so for your building background today, remember this is the part that everyone should feel confident doing. I'm going to time you for 30 seconds. And you're going to list as many types of numbers as you can in 30 seconds. So that may be some decimals, some fractions, some positive negatives. I want you to list as many as you can. 30 seconds. I'm going to keep the timer going, so don't hit pause. Ready, go. Yep, keep writing. You're doing great. I know you know more numbers. Fill that whole space. 10 more seconds. 2, 3, 2, 1. There we go. Okay, so you should have this whole thing just filled out with lots of numbers. And we're just getting that brain going. So I'm not even going to go over any. I'm going to trust that maybe you have a fraction in there. Hopefully you have a decimal if you don't, sneak one in real quick. And some positives and negatives. Today our idea kind of built around the book, If You Give a Mouse a Cookie. So we're going to listen to that book really quick. And then we're going to fill out this visual aid.
If you give a mouse a cookie, he's going to ask for a glass of milk. When you give him the milk, he'll probably ask you for a straw. When he's finished, he'll ask for a napkin. Then he'll want to look in a mirror to make sure he doesn't have a milk moustache. When he looks into the mirror, he might notice his hair needs a trim. So he'll probably ask for a pair of nail scissors. When he's finished giving himself a trim, he'll want a broom to sweep up. He'll start sweeping. He might get carried away and sweep every room in the house. He may even end up washing the floors as well. When he's done, he'll probably want to take a nap. You'll have to fix up a little box for him with a blanket and a pillow. He'll crawl in, make himself comfortable, and fluff the pillow a few times. He'll probably ask you to read him a story. So you'll read to him from one of your books, and he'll ask to see the pictures. When he looks at the pictures, he'll get so excited he'll want to draw one of his own. He'll ask for paper and crayons. He'll draw a picture. When the picture is finished, he'll want to sign his name with a pen. Then he'll want to hang his picture on your refrigerator, which means he'll need Scotch tape. He'll hang up his drawing and stand back to look at it. Looking at the refrigerator will remind him that he's thirsty. So he'll ask for a glass of milk. And chances are, if he asks for a glass of milk, he's going to want a cookie to go with it.
I'm trying really hard not to laugh about that. Whew. That guy's accent. Something different. Alright, so that was the book. So we're on this part, if you give a mouse a cookie. So this inside circle is what we started at. And so the idea was we first gave this mouse one cookie. Then we're going to build on that. After we gave that mouse a cookie, the next thing he asked for was milk. After we gave that cookie a milk, he wanted a mirror because he wanted to see if he had a milk mustache. So I can assume if I walked in your house and I saw you giving a mirror to a mouse, I could make the assumption that, yep, you've given him milk, and yep, you've given him a cookie. After he looked at the mirror, the next thing he wanted was a nail clipper because he wanted to trim his hair. I'm sorry, I didn't know that guy's voice was gonna... Okay, so he asked for a nail clipper. And after the nail clipper, he wants a broom. So when my niece is reading this book, she's 3, so really when my brother's reading the book to her, if I walk in the room and he's at the part with the broom, I know that on that page, that at that point in the story, the mouse has already gotten the nail clipper, he's already gotten the mirror, he's already gotten the milk, and he's already gotten the cookie. So it starts on the inside and it builds its way out. If I know that he has the broom, I can work my way in and assume he's all of those things. So this, you're probably like, what the heck, Miss Morrell? What are you talking about? Okay, but here's the deal, is that this is going to be directly related to our idea today. And our notes are going to pick up real fast now, so pay attention. Alright, so here we go with our first example. Our first example is asking for identifying the natural numbers. If you have a highlighter nearby, take that highlighter and highlight that word, natural numbers. That's a classification. That's a way that we can call numbers. Okay? So natural numbers are numbers we use for counting. If I was going to count students in my class, I would say you're student 1, you're student 2, you're student 3. So I start at the number 1 and then I count numbers higher than 1. So my first number here is 1. So if I was counting students, I would start with the number 1. So that is a natural number. So that works. Okay, square roots. For square roots, we're going to want to look at our multiplication chart. We're going to be looking at this middle column, or the middle diagonal. So 1 times 1 is 1. So we're looking at 1, 4, 9, 16, 25, 36. So what 6 times 6 is 36. So that's a number that we want to look at. 49, 64, 81, 100. Notice 23 is not one of those middle numbers. Okay? If it helps, you can take a highlighter and highlight those numbers. So I'm going to zoom in on that. And let's highlight these middle numbers because these are perfect squares. So we're going to highlight 1, 4, 9, 16, 25, 36. We just go down that diagonal, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, 400, and 441. So those are those numbers that are perfect squares. Those are the ones we want to keep in mind. Is 23 one of them? Nope, I don't see 23. So that means that it's not a natural number because there is no perfect square root of that. So we're going to cross that one off. I want it to stay red. Okay, when I would count students, I would not count negative 4 and 4,700 students. I also, when I usually start counting, I don't start at the number 0. So if I was going to count how many students are in this class, I wouldn't say 0 students, 1 student. I would just start at 1. So 0 is also not a natural number. I also would not use this really long decimal when I was counting, so not that one. I would not normally count 2.5 students. Now, square root of 25, that square root, we're going to look at this. 25 is one of those numbers we highlighted. It's right here. So square root of 25 is 5 because both those sides say 5. Okay? So square root of 25 is actually just 5. Is that a number I would count? And the answer is yes. If I had 5 students, I would count 5 students. I would not count a negative 17 because when I'm counting things in front of me, I don't count negatives. I would not count a pi amount or these decimals. Would I count 6,823,192? The answer is yes. If I had that many things in front of me, if I was patient enough, I would count that number. So those 3 are numbers that we use for counting. What other numbers could you use for counting? We could use the number 17. We could use the number 29. We could use the number 372. Try and come up with one more number there. What's a number that you would use to count? Okay, number 2. Number 2, it says identify the whole numbers. So whole numbers are positive numbers positive natural numbers is actually what we should say. Sneak in that word natural. I'm sorry. Positive natural numbers and 0. So it's really what we already did. It's like that cookie. We already did the cookie. Now we're going to do the milk. Okay, the only thing we're adding on is 0. So we're going to keep these exact same numbers we've already boxed. Those 3 are already it because this includes these. Okay, so a whole number would be 1. Square root of 25, because that's really just 5, remember. And 6,823,192. But it's also those numbers and 0. So we're also going to include 0. That's the only difference, is that 0 is included. So all these other ones, I'm going to X out. They are not whole numbers because they have decimals in them or they're written as fractions. Okay, so my example. So a big thing that we want to make sure is with whole numbers we can include 0. And then any other number we already mentioned that you could count. So 36, 72, 1,962, anything like that. Go ahead and make your own if you'd like to. And then we're going to move on to the back page. Okay, back page. Defining the integers. So again, we're going to go back to the idea of whole numbers. Integers are whole numbers and their opposites. Whole numbers and their opposites, meaning positives, opposites are negatives. So since it's that whole numbers, I can scroll up because I can if you want to flip it over. It's going to include all those 4 numbers we already boxed. Same thing. 1, 0, square root of 25, because that's really 5, and 6,823,000. So the only thing I'm looking for now is that those are positives and 0. Are there any numbers here that are negative that would be a negative of what we would count? So square root of 23, again, we don't know that yet, so we wouldn't count that one. We wouldn't count a decimal. That one's positive, so not worried about it. Positive, we would have already counted it. Negative 17. Is that opposite of a number we would normally count? And the answer is yes. We would normally count the number 17. This is opposite because it's a negative. Opposite of a positive is a negative. So now that is included. Pi is a decimal, so we would include that. And same thing with 1 and 48/100ths repeating. So X these out. They do not work. All All right, so my examples. So this could be any, what we call like positive or negative, and we like to think in our brains like whole numbers, but it's not really whole numbers. They're integers. Okay, so I could have negative 26. I could have negative 42. But also an integer would be like the number 5, or the number 10, or 0. Those are all integers. Okay? Next one is identifying rational numbers. So rational numbers, rational numbers are the integers, fractions, and decimals that end or repeat. I might have to zoom in here because I didn't really save myself enough room. Decimals that end or repeat. Okay? So decimals that end or repeat in fractions. So it is integers. So just like that, give a mouse cookie. We're going back to what we did before. We already had these 1, 2, 3, 4, 5. These are ones that we're going to include because this includes integers, and these are integers. Okay? So I'm going to box the 1. I'm going to box the square root of 25 because remember that's really 5. Negative 17, that's an integer. 0, and that's 6,823,192. Okay, now I can include fractions. So do you see any fractions here? Here is a fraction. A fraction is a part of a number, so 1 over 2. This part is a fraction. So this is a mixed number. So that mixed number would be a rational number. Okay. Another thing we have is decimals that end. So do you see any decimals that end? And that would be this one, because it stops after 7. So there's a decimal point. So it's negative 9 and 47 hundredths. It stops after that 7. So that is a rational number. Okay, and then any decimals that repeat. Usually for repeating decimals, we use that line to show it's going to go on forever and ever, but it's repeating. So this 1 and 48 hundredths really means it's going to be 1.488888888 forever and ever and ever and ever and ever. If I was going to say that whole number, I would be saying 8 over and over and over again until I die, because it keeps going on forever and ever. And then somebody else would have to continue it. Okay, this one up here looks like it repeats. It goes 4, 1, 4, 4, 1, 4, 4, 4, 1, 4, 4, 4, 4, 1. But there's no place where we could use that line where we're going to say it's going to continue to repeat over and over again, because we keep adding in a 4. So that one doesn't work. Okay, so here we go with our examples. Let's put the number 3, because that's an integer. We can put the number 0, because that's an integer, and rational numbers include integers. We could have negative 1 and 3/4, any sort of fraction there. We could have 6 and 27 hundredths. We could have 3 negative, let's say negative 3, and let's do 14 hundredths. But I'm going to put that repeating sign over the 1 and the 4. What that means is that would go back 1, 4, 1, 4, 1, 4, 1, 4, 1, 4, 1, 4, 1, 4. It would keep going over 1, 4, 1, 4, 1, 4, 1, 4, 1, 4. Okay, now this is the one that's a little separate. All right, so irrational numbers, they do not include the rational. So this is where it's not like they give a mouse a cookie. Okay, so irrational numbers are decimals. Oops. Yeah, let's write it in a different color because this one's different. Decimals that never end and never repeat. Okay, so they never end, they keep going on forever and ever and ever and ever and always, and they never repeat. So 1 ends, so 1 is not irrational. Another word for irrational is it doesn't make sense. So a number that really doesn't make sense to us sometimes is pi, because pi keeps going on forever and ever and ever, and never repeats, and it never ends. Okay, now this example with the 4 and the decimal, this keeps going on forever and ever and ever, as far as we know, because of this dot, dot, dot. And it doesn't technically repeat because every single time I'm going to add in another 4. That's the pattern. 1 4, 2 4s, 3 4s, 4 4s. So next time it'll be 5 4s, then 6 4s, then 7 4s. So I can't ever use that line. So this would be another example of an irrational number. The last one is going to be when we go back to that multiplication chart. All right, here's my multiplication chart. Remember those square roots? This square root of 23, it wasn't perfect. It's not one of those ones that we highlighted. So because it's not one of these ones we highlighted, that means it's going to keep going on forever and ever and ever and never repeat. If we put in our calculator, it would give us an approximation, but that's going to keep going on and on and on and on and on and on and on forever and ever and ever. Okay, so our examples of this are generally square roots. But you're going to pick any number that's a positive that is not one of these. And don't go higher than this because we don't know what the next one is. So let's say 52. 52 is not on here. So the square root of 52 would be irrational. How about the square root of 7? None of those highlighted parts is 7. So that would work. Okay, try and come up with another one. Square root of, and it can be any number except for these ones. Okay, come up with your own. Okay, last example is real numbers. Real numbers are natural numbers. They're whole numbers. They are integers. They are rational. And they are irrational. Right now, I'm going to take a guess that most of you only know real numbers. There is such a thing as called as imaginary numbers, but we're not on that yet. Okay? I'm going to take a guess that most of you are thinking about just rational numbers, or real numbers, I'm sorry. Okay, so each of these ones are natural. 1 was natural, and the square root of 25 was natural. Okay, whole numbers included that number 0. Integers were that negative number that is like a counting number, but it's negative. A rational number are the decimals that end, or a fraction, or a decimal that repeats with that line, keeps going on and on. And this includes irrational, so those numbers that go on forever and ever and never repeat. So right now, this is literally any number you can think of. So 2, 19, I'm just coming up with these off the top of my head. Negative 36, square root of 41. I don't know what that is, but it's real. Okay? All right, for our summary, we're going to fill in this visual aid just like we did with the Give a Mouse a Cookie. The very simplest numbers that we have are our natural numbers. Remember, natural numbers are like our counting numbers. This was a parenthesis, I know it's hard to see. After natural, we have whole numbers. Whole numbers include the natural numbers and 0. Okay, then we have integers. Integers are whole numbers and natural numbers, but now it can also include negatives. Negative numbers that are the opposites of wholes. Then we have rational numbers. So if you know you have a rational number, you can say it's also an integer, it's also a whole number, it's also a natural. And rational are fractions and decimals that end or repeat. Try and fit that in, sorry. Our other group that does not overlap at all is irrational numbers. Irrational means they don't make sense. So numbers that don't end and they don't repeat. But all of these numbers, so that's why I have that box around all of them, all of these numbers are what we would call real numbers. Alright, this video was a little bit longer than most videos will be because we had that story. And this was just a lot of vocabulary. So normally it's not quite this long, but it is today. I apologize. Okay, bye!